Yeah, good morning. In this session, I would like to show you a typical flow sheet simulation, and in addition, we are also required to do certain sensitivity analysis. Analyze the process performance by changing certain critical parameters. So all the required information is available, the conditions, operating conditions, and necessary details. Essentially, we will be looking at doing mass balance on this flow sheet, though you are also going to perform energy balance. The major concentration is going to be on mass balance and analyzing the performance of this particular flow sheet. So the feed stream, which is a mixture of propane and propylene, at these temperatures and pressure, having this flow rate is entering into the mixer. The recycled stream is getting mixed up with the fresh feed. The combined feed is going to enter into a reactor, which may be operating at 200 degrees centigrade and 20 bar isothermally. And the exit is going into the heater, wherein the outlet of the reactor is cooled to the required temperature at which the flash column is operating, and you will also be reducing the pressure. Then the product is separated by the flash column. The unconverted gases, before they are sent in the form of a recycle, a small fraction is purged because you have an inert which is not taking part in the reaction. So in order to avoid the build-up of this inert, we are removing some small purge. Because there is a reduction in pressure, we wanted to compress it back to the required pressure of 20 bar by using a compressor. So first of all, let us try to simulate this problem and look at some analysis with respect to its performance. So let us go back to Aspen. So the first step is to define the components. So we have, just one second, propane, propylene, and you are going to form one hexene, right? This is the product. So let us define these components and then try to define, try to take a property model, define the flow sheet, draw the flow sheet, and then provide the necessary information. So let us go into Aspen. So we have propane, which is an inert material, propylene, then we have the product 1-8C. So having defined the components, go to the next input step by pressing N. So choose a property model. As long as you are interested in mass balance, you can choose any property. It will not be affecting your mass balance results. Go to the next input screen, go to simulation environment, and create your flow sheet as described in the problem statement. So initially we have a mixer. The combined feed is going to enter into your reactor. Remember, we don't know the kinetics of this chemical reaction. We know the conversion. So the only option for us is to make use of a stoichiometric reactor, mass and energy balances, then followed by you have a heater, wall, flash column. So let me add these blocks. We are not interested in doing designs. Maybe after doing this energy mass balance, each of these units you may be able to replace with appropriate models that can go into design calculations. Then followed by valve. So the valve is available in pressure changers. So this is the valve. You can probably increase its size. Then followed by a flash column. Then you have a splitter. Then a compressor. What we have, for convenience, let me rotate. So let us try to provide the input and outputs. So the feed stream, then the combined feed is entering into a reactor, then the reactor exit is cooled, then it is entering into a pressure reducing valve to decrease the pressure. So you have a bottom product, the unconverted gases are sent into a splitter, small fraction is purged and the remaining is compressed, and this is again sent back to the mixer. So you have probably I'll name a few typical streams. So this is your feed and this is your recycle. Then this is your punch. This is your product. Okay. So we may require this. Let me rename this. This is flash input to the flash, and this is vapor product from the flash. Or flash out, because we already named the other stream as product. So after drawing this flow sheet, now you can go into the next input step. But before you go into the next input step, you can analyze what are the streams that you need to specify. If you take an envelope surrounding all these blocks, you can see that only feed is entering into the process and there are two output streams, purge and product. So remember, all these models will be able to perform rating calculations. So given the feed stream, operating conditions and equipment parameters for all these units, you should be in a position to calculate the purge and product streams. So if you try to look at this, now you can see only information with respect to feed is being asked for. So you don't have to provide any intermediate stream, and some information with respect to all the blocks that you have. You know that mixer doesn't need any specifications, but all the other blocks we may have to give the required information. Anyway, we can go in a step-by-step manner by pressing this next. So we are being asked to provide information with respect to the feed 150 degrees centigrade and 20 bar. 50 degrees centigrade, 20 bar, and the feed is coming at the rate of 1000 kilomoles per hour. Is it so? Yeah, 1000 kilomoles per hour. And the mole fractions of the feed, the composition of the feed, 2% propane and 98% propane. This is the fresh feed. So we have defined feed, so we'll be able to input step. This is with respect to the reactor. The reactor is given that it is operating isothermally at 200 degrees centigrade and 20 bar. Next, define the reaction stoichiometry. So propylene, 2 moles of propylene are giving rise to 1 mole of 1-hexene. So the product is hexene coefficient 1. And we were given that the conversion is 80% with respect to propylene. So specify that. The fractional conversion is 0.8 with respect to the component propylene. Say next. So we have specified the reactor as well. So you can go to the next input step. Now we are being asked to provide information with respect to the heater. And the problem statement says the exit temperature of the heater must be 120 and the exit pressure from the valve should be 12. So let us provide this information as well. 120. And if you don't say anything with respect to pressure or put 0, we are presuming that there is no pressure drop, right? You don't have to, you can say either 0 or 20, it means the same. So we have specified this heater block. Then we are talking about the valve, adiabatic flash, outlet pressure is 12, that is given to you. So go to the next input. Now the flash column is also operating at 120 and 12 bar. So we have defined this. Then the split fraction with respect to purge, I think 5% is purged. No, 2% is punched. So specify that. Next input step, compressor. We want it to compress it back to the original pressure of 20 bar. So you can see all the required input is complete. So we should be able to run the problem. So there are some issues with respect to the compressor. What you can do is go to the compressor. Now you look at convergence. So it is performing vapor only, but performing vapor liquid check. So if you strictly say vapor only and reset, the calculations, the errors warnings will be going. Yeah. Now you can see we had no warnings or no errors, but there is a loop of calculations involving all these blocks. Why this loop? Why this iterative process? We have already observed. Usually when you draw a flow sheet, what is the first step that you need to do? You need to check whether I should solve this as a single problem, or is there any possibility for me to divide this into partitions? Do you think it is possible? You can see that the recycle is involving, it is initiating from this block. In between we have B7, B1. So between this recycle loop is going to involve all the blocks B1, B2, B3, B4, B5, B6, B7. So it is not possible to divide this into two problems. Now, you can also see from the control panel, by default, whenever there is a recycle, there will be a tear stream. What is the stream that it has decided to tear? Recycle stream. So because it has decided to tear the recycle stream, you know already what is meant by tearing, guessing values for this recycle. Having guessed values for this recycle, because you already are providing information for the feed, both the input streams are known. So you will be able to solve block B1, then B2, then B3, B4, B5, B6. Then by the time you solve 7, starting with an initial value, we got an updated value. Compare whether the updated value matches with the previous values that you have guessed. Otherwise, you start with another assumption for recycle and proceed with one more iteration. So, conventionally, if you are solving this kind of a mass balance problem, I don't think we'll be doing this in this particular fashion. But this is the problem that we'll be encountering while doing process simulation, because all the models are capable of doing only rating calculations. So this is the penalty. Now, we're able to come to a convergent solution, and the method by default used is Weisstein. I think you know what is meant by Weisstein method. See, generally, you started with an initial approximation for recycle. And when I get an updated value for this recycle stream, we compare for convergence. Otherwise, we need to start with a fresh set of values for this recycle stream. Remember, guessing values for recycle means guessing values of C plus 2 variables, depending on the number of components. How many components do you expect? All the 3 will be present. So at least you are required to guess 5 values. So temperature, pressure, composition, whatever are those 5 variables. So normally, Aspen will be making these initial guesses with respect to any recycle stream or tear stream as the component flow rates are presumed to be 0. So C variables are taken care, and the pressure is assumed to be 1 bar, and the molar enthalpy is taken to be 0. So these are the 5 guesses normally the Aspen will be making, right? So given these, you can go back to control panel. Now you can see 5 variables are. Why this 5 is coming into picture? Because there are 3 components. 5 variables are guessed. Until all these 5 variables come to a convergent solution, you need to go with this iterative process. So by the time you complete about 8 iterations, 3 variables have come to convergence, but 2 variables did not come to convergence. So you go on doing this until all the variables come to a convergence. By this time, I think 1 variable is left. So by completing 13 iterations, we were able to come to a convergent solution. Now, the present values of recycle, if you replace them with if the previous values of the recycle, if they are replaced our latest values of the recycle, we call this process as successive substitution. Unfortunately, successive substitution is slow in rate of convergence. So this method is convergence promotion technique. If you want some details, you can go into literature and see how it will be able to improve the rate of convergence. So we got to our results. As you can see, you will be able to identify from the stream summary the information about all the streams involved in your problem. So we were able to make some calculations. Instead of this, it may be better to go into each and every model and observe the results. What we are generally interested is, of course, you can see from each of these blocks. Now, I would like to see the flashcard stream results. So all flash in, this is the vapor product going from the flash, this is the liquid product going from the flash. So typically, if you look at the mole flows, this is the amount of propane that is entering, and 44 kilomoles per hour of propane is going into the vapor, but some amount of propane is also absorbed in the liquid product. Similarly, you can see what is the propylene and what is the product that you got. Out of 580 kilomoles per hour of product that you are getting, only 453 kilomoles recovered into the product stream. This 127 is going back in the form of recycling. So if you look at the composition, we were able to get a purity of about 84%. And the flow rate is 537. This is the amount of product that you are able to get with a purity of 84% HCl. Right? So similarly, in the same way, you can, whatever information that you want, you should be in a position to see. For example, I would like to see the recycle. Remember, 1000 moles is the fresh feed, but what about the recycle? 328. The recycle ratio is 328 by 1000. So about, you can see this recycle is not very huge because we had a good conversion of 80%. Now if you want, if there is a possibility, you can think of varying this conversion beyond 80 and see how the process is going. Now, one major issue that we have, I think you can just analyze and also try to do other sensitivity if you are interested. But typically, to give you an idea, trying to look at the temperature and pressure at which the flash column must operate, or keeping the pressure constant, I am varying the temperature and observe what is the purity, what is the product flow rate, what is the recycle rate, and what is the fraction recovery. What do you mean by fraction recovery of C is out of the product that is entering HCl column, how much fraction of that is recovered into this product. Ideally, I would like to get all this product that is coming in into this particular stream. Now let us try to apply some sensitivity study. So the sensitivity is available in model analysis tools. Expand this, click on sensitivity, say new. So in the first case, we are keeping the pressure constant and change the temperature. Remember, the temperature should be such that you have two-phase region possible in the flash column. As and when you, whatever values that you want, you may not be in a position to have the two-phase region. Anyway, you can check it up from the simulation. So vary. What is that you are trying to vary? The temperature at which the flash column is going to operate. Right? Say new. It's a block variable because we are varying the temperature at which the flash column is operating. The block is, this is B5. And the variable is temperature. In fact, I don't have an idea about its boiling point, its bubble point and dew point. And this bubble point and dew point, between that you will be able to vary the temperature. Let me start with 110 degrees centigrade and maybe 140 degrees centigrade. Remember, the pressure of the flash column is kept constant. In fact, in the case of a sensitivity block, you will be in a position to vary any number of variables, but for convenience, I am only varying one variable. So maybe increments of 5 degrees or whatever you wish, you can specify. So we have defined this vary variable, and what is that we are trying to observe? So according to this, purity of the product. Purity. What kind of a variable is this? This is the mole fraction of one hexene in the product stream. So let me select mole fraction. The stream is product and the component is one hexene. So by varying the temperature, we would like to see what is happening to the purity of the product. Similarly, we would like to find out what is the product flow. That is also one variable. What is happening to the product flow, right? So this is also a stream variable. Stream mole flow. Now, if you are looking at the total flow, you need to go to stream variable. Then select the stream, which is the product, and the flow we are interested in is maybe mass flow or mole flow. So this is the second. So purity of the product flow rate, recycle rate. So we would also like to look at the recycle flow. So the recycle flow is also a stream variable. Stream is recycle, variable is mole flow. So this is going to show you recycle flow rate. Finally, I think we also are required to find out the fraction recovery of product, right? What I said with respect to this fraction recovery of product, the amount of hexene entering into the flash column and the amount of hexene leaving through this product divided by the amount of hexene entering through this inlet. That is what is meant by fraction recovery. So in order to do this, I need two variables. What is the amount of hexene entering into the column? What is the amount of hexene available in the product stream? That ratio I would like to see. So let me define another set of variables. So hexene into the flash column, I mean. So this is also a stream variable. Stream is, it is stream variable. Stream is flash in. We wanted to identify the mole flow of hexene. Selecting this as all. Maybe mole flow in flash in with respect to hexene. So this is going to represent the amount of hexene entering into the flash column. What is the amount of hexene leaving through the product? So I would like to look at the mole flow of hexene stream. Again, to select this mole flow. Then say next. See, in this sensitivity, we are varying one variable, the temperature, but we are trying to look at what is its effect on several measured variables, right? So you can have as many measured variables as you wish, and also in the case of sensitivity, you will be able to vary any number of variables as well and observe their effect on these purities. So let say simply fill variables. So all the variables that you have listed will automatically come, but in fact we don't have the ratio. Now I would like to define this ratio as x out divided by x in. In fact, because we have already defined, if you want you can keep, but I would like to even remove this. This also I will remove, and I would like to, I'm interested in looking at the ratio itself. X out by x in. So these are the four variables that I would like to do. So having defined this sensitivity, now I would like to run it. Now you can see there is already a loop of calculations in order to converge your recycle. Now, in addition to that, for every temperature that I am using in the sensitivity, this recycle loop should come to a convergence. So you can see the various calculations that are done. Anyway, you can have a look at the results of your sensitivity. Now, because remember, we are keeping the pressure constant and we were able to change the temperature from 110 to 140. Now, keeping the pressure constant, what is happening to the product purity? It is increasing, right? So, in order to get more product purity, it is always better to increase the temperature. But what is its effect on product flow? You can see the product flow is decreasing. What is happening to the recycle flow? With increase in temperature, the recycle is also increasing. And what is happening to the recovery? We were able to recover, recovery is, remember, the amount of hexene that was recovered into the product stream compared to the amount of hexene entering. So 86% of the hexene entering into the flash column, we were able to get it in the bottom product, liquid product. But as you keep on increasing the temperature, the recovery is reduced. So there are some advantages, there are some disadvantages. On one side, increasing the temperature is improving the purity, but the penalty that you are that is going to increase your recycle flow rate, that is also going to decrease the product flow, and the recovery is quite small. Unnecessarily, if you are recovering about 48%, 52% of the product is finding its place into the recycle. Unfortunately, this is going to increase the size of the equipment, right? So this is how you will be in a position to vary the sensitivity. Now let me, because remember we are operating the flash column at 120 degrees centigrade. Now what will happen? I would like to see, keeping the temperature constant, what will happen to the pressure, right? So let us try to modify this sensitivity. Now I am trying to vary, instead of temperature, the pressure. I not have much of a variation. Let us say 10 to maybe 15 bar in steps of 1. Provided at 120 you have two-phase region available within this. Change I am making, I would like to rerun the problem. Maybe reset and also rerun. Now look at the results. So we were varying, we were increasing the pressure, keeping the temperature constant at 120. So what is happening as you keep on increasing the pressure? What is happening to the purity? It is decreasing. But what is the advantage? You are able to recover more, the recovery of hexene in the product stream is improving. As you keep on increasing the pressure, the recycle flow rate is decreasing. And the product flow also is increasing. Now, do you think you will be in a position to identify what is the best temperature and pressure analysis? Unfortunately, we may not be able to do that unless and otherwise we go into some kind of cost estimation. Now, let me once again modify this problem, and I would like to vary, the pressure is already there, so I would like to vary another variable, temperature. I would like to see the effect of varying both pressure and temperature in the same sensitivity. So this is again a block variable. Block is, which one is this? B5. Flash is B5. Temperature. We said it is from 110 to maybe 140 in steps of 5. Just 1 second before I run this problem. From the previous results, if you want, you will be in a position to see the results back. You can check. You can check, for example, each of them separately or all of them together. So this is how the product purity is varying with pressure. As you keep on increasing, the mole fraction of one hexene in the product is coming down. So in the same way, you can select all of them. So you can see the graph should come anyway. Able to see graphically what is happening to all these variables as a function of pressure. Right? You will be able to see that as well. Now, having included the second variable, now we need to run this problem. So remember, the pressure is varied between 10 to 15 in steps of 1. The temperature is varied in steps of 5. So there were some errors. Let us see. You still will be able to get some results. This is because, be careful, we may not be having a two-phase region in all these possible combinations. So because we were generally giving the temperature and pressure, the error may be because at 10 and 140, you had some problem in reaching a convergent solution with respect to the flash column. But anyway, you will be able to see the trend. For example, remember, the pressure is varied from 10 to 15, the temperature is varied from 110 to 140. So for all possible combinations of the pressure and temperature, the calculations are done. So usually it does keep the pressure constant, vary the temperature and see what is its effect. Then increments the pressure, once again go on doing this calculation at this pressure for all temperatures. So for each of these pressures, the temperatures are varied and we are trying to observe how the flow rates, purity, fraction recovery is going to change. So remember, these are too many calculations. Now I would like to just show you one more simple example which might be useful for practice. For example, I don't want to list out all possible combinations. I would like to look at when the temperature is 105, 10 is the pressure, 105, 12, 120, 12, 130, 12, 140, 12. Now, do you think I'll be able to do a sensitivity study? Suppose if I want to increase if I want to define the increment, now there is no increment with respect to temperature between these 2 points. Here the increment is 15, here the increment is 10. So we will not be able to do these calculations in general without having to make unnecessary calculations like what we did. So how are we going to handle these values of temperature and pressure? I wanted to observe all these variables. So if you have this kind of an issue, what you can do is, let me close some of the unnecessary things. Yeah, go into S1 input, right? Click on this case study. By default, it will not be on. So click on this case study. Then you need to define the cases. In other words, go to next. So what is the case? 1, probably the first case. You can say anything. So the first variable that we have defined is pressure, right? You can see in the first variable is pressure, the second variable is temperature. So I am trying to, what is the first value of pressure that I am interested in? 10. Temperature is 105. So define those values explicitly. 10, 105. This is the values of pressure and temperature at which I would like to see all these variables. Now, what is the second case? Again, I think 105, 12. So define this. The third case is, onwards it is 12 in all the cases, but the temperature is 120, 130 and 140. Let us put these values. 12, 120, and the fourth case is 12, 130 fifth case is 12 and 140. Right? So we have defined cases instead of varying in general. Okay, let me reset and run this problem. Yeah. Now you can see the results of your sensitivity, specifically only at the specified cases of these variables, the variables, whatever observations that you want are listed. 10 105, 10 105, 12 120, 12 130, 12 140, 12 120. Out of all these available sets, now which is giving you the best product quality may be this one. If you are operating the flash column at a pressure of 12 bar and 140, you are able to get the maximum purity, right? But the disadvantage is it is going to reflect the minimum recovery. So you should be able to pay this penalty and handle a large amount of reflux, and also the product flow is going to decrease. Whereas if you try to look at the best recovery, I think it is happening. Sorry, I did 10 105 both cases. Is it like that? I should have given this also 12. That's why it was repeating. Anyway, so you can see the best recovery is happening at 84. The advantage is you had the minimum recycle, maximum product rate, but the disadvantage is you are getting low product purity. Right? Similarly, if you want to handle the lowest value of reflux, these are the conditions. Highest value of product purity, these are the conditions. Now you need to probably come to some kind of a compromise between maintaining product purity and maintaining a particular recovery. In order to gain one, you may have to lose on the other aspect. It may not be possible for you to identify, it cannot be possible to get all of them at optimum values, right? So this kind of analysis can be done, even though the flow sheet seems to be simpler. Now, the major decision is what is the temperature and pressure at which you need to operate the flash column, which is going to affect the product flow, product purity, recovery, recycle rate. All these variables are going to be affected by this product purity. In the same way, if you would like to, in case if you know the kinetics, and if you want to use a bigger reactor so that you will be able to, or maybe at a higher temperature, so that the conversion can be improved, even that you will be able to study as a sensitivity. Now, with this kind of comments, I would like to close this session. Feel free, once you create this kind of a flow sheet model, you are at liberty to check, do sensitivity analysis on the process with whatever variable that is going to affect your products.